Hello, so today we are going to do this Leetcode problem. It's part of Leetcode Daily April Challenge. It's design hash map, so the problem wants us to design a hash map without using any built-in hash table libraries. So no collections and no map, just no dictionaries, libraries. And we want to design it such that we have a constructor or an initializer that initializes the object with an empty map. We want a put function that puts a key, at key puts a value, which basically inserts key value pairs into the hash map. However, if the key already exists, we want to return we want to update the value, basically change the value to be the new one. And we have get function, gets past the key, returns the value. If it doesn't exist, we need to return -1. Remove key, which removes the key and the value, if they exist, of course. Okay, and that's pretty much it. So we have a couple of examples here. So we initialize our first, and then put for putting 1 and 1, key 1 and value 1, and then we put on key 2, value 2, and then we get 1, key 1, so that should return 1. That's what we have here. And then we have get 3 doesn't exist, so we return -1. So pretty much the same as the description. So how can we solve this? The simplest thing to do actually is to just use something here in the constraint that says that we have key and values are between 0 and 10 to the power of 6, right? So we can just create an array that has size 10 to the power of 6 plus 1, right? And then that way we guarantee that all the keys will fit in the array indices, and we can basically just do array of key is equal to value each time. So that's the simplest solution. It's definitely not ideal because it uses a lot of memory, but we can quickly see what it looks like. So I'll just paste it here since it's very simple. So basically we create a list. We can initialize it with values -1 because the problem says that the keys and the values are between 0 and 10 to the power of 6. And so we initialize with -1. And then for put, we just update the value. Okay, if key already exists, then we will update with the new value. If it doesn't exist, then we will set the new this position in the array to value, right? And get just returns that position in the array, which would be correspond to key. And remove will set the values at key to -1. So that would be removing. So that next time get will return -1 if the key doesn't exist, which is what the problem asks us to do. So yeah, pretty straightforward. However, it uses a lot of memory. Even like if we have very small keys, we'll end up allocating 10 to the power of 6 plus 1 array. Yeah, so we saw the idea of just using an array, but that is too expensive in terms of memory. So let's see how we can improve on that. So this is an idea where we can use buckets. And so something like this. This is similar to design hash set problem. So for each bucket, we can have a list. And we can decide what to put in this list. So in the list we can put a key and a value. And that way basically, okay, let me give more space maybe so that we can have a little bit more here. So something like this, okay? And for each space in the array we can put a key and a value, a tuple essentially. And that way we can put multiple. So we can map multiple key values into the same spot. And that would mean basically in a smaller space, in a smaller array, we can put more key and value pairs. And so for example, let's pick an array here of size maybe 1000. Okay. And we want to fit 10 to the power of 6. And so we'd have our keys here. And then what we'd have is, let's say, K1, V1 values, and maybe another one, KI, VI, let's call this KJVJ, right? So these two may map to the same position, and so in that case they would be in a list like this with KI, VI, and then KJ, VJ, right? Okay, and now to find, now how can we actually implement the different operations? So for put, what we'll do is we need a way to map this key here to this position. So this is 0, 1, 2, okay, in a way that we don't utilize more than 10. The simplest way to do that is to do just key modulo the size, which is 1000. What this will allow us to do is, for 0 it will map to 0, when key is 0, when key is 1 it will map to 1, but when key is more than 1000, let's say 1002, then because we do modulo equal to 2, it will map to this one here. So we'll just add it to the list. So you can imagine if we have a key with value 2 and a key with some value x1 and another key with 1010 here, 1002 here, just because both map to the same position. So we'll have a list like this. So this is the main idea. So with put, what we need to do is, the first thing is to find the bucket index, and so we'd have our bucket would be just, so this array here, we'll call it buckets. And so for put, we'll just take buckets in this index, so our index would be just key modulo 1000, and so the buckets array will go to that index, and if the value is not there, then we will just add to the list in that position. What would we append? We append the pair, so we'll append, this is for put key value, we'll append the pair key value. But if, so this is only if it doesn't exist, if key not in bucket yet, right? But if the key was already there, what should we do in that case? Well, it should be pretty simple. We just need to find the index in this list of the keys, so let's say it's here, and then we can replace the value. So we need to find the index I in the bucket, so we need to implement a function that does that. So let's call it find in a bucket, which is our bucket here is bucket's index, and we need to find the key, and that we can do just by going through, iterating through the list and finding the key that equals to our key here. So just our key is just k. So we just need to find the key that equal, for example, to 1002 if that was the key we are looking for, right? And once we found it, we just return the index. So that's what the find function will do. And in that case, we'll just do buckets at index at position I is equal to value, or v, right? So this is if the key is not in the bucket, and this is if the key is in the bucket. If key exists already, we'll just update the value. Okay. So here, since it's a key value pair, it needs to be equal to kv. Okay. So that's the put function. Now what about get? So for get, same thing. We need to get the index here, the same index that we got here. Let's just copy this over. Now when we get the index, we need to find the value, right? So we'll do a similar thing like we did here. We'll get the position first in the bucket, and then we will need, so this is get, so we'll need to find the value, which is going to be just, again, buckets at this position. So this will give us a key value pairs. Okay, sorry, let me just write it out. So it will be buckets at index, right, and position I, and to obtain the value, it's at position 1 in the tuple. This is 0, 1, so it's position 1. So we can just return this. Okay, so what about remove? So for remove, we just get past the key. So for remove as well, it should be pretty straightforward. We just get the index and find the position, right? So something like, oh, sorry, something like we get all of this, and then we check if the element exists. So we have find returns as -1 if the element doesn't exist, and so we check if it's different than -1. We can just use delete in Python to delete the element in the bucket that is at that position I. And that's pretty much it. Now in terms of, if we take a look like at the time complexity of what we used here, so for put, find will go through the content here of the bucket size. And otherwise we are doing O of n, and this one is O of, oh sorry, this is O of 1 here, and this is O of 1, so it's only the time complexity of find. So find, it's at most, if we call this size, right, then it's n, which is the number of elements divided by size, because that's the most that this list can contain, and this is linear in the size of the list. So find would be O of this. If we call this k, then find is O of k, and so put is also O of k. For get, same thing. The expensive operation is find, the rest is straightforward, so it's O of k. For remove, this is also O of the size of the bucket, because deletion this way is O of n, and it's the size, so it's O of k as well. Okay, k being n divided by size. Yeah, so that's pretty much it. So let's code this solution up in a more cleaner way, and see if it passes our test cases. Okay, so let's see how we can apply what we just saw. So first we need our size that we said is, we are going to go with just 1000. It's not really important the number you choose here, except like if you choose very small number, then obviously it would have more collisions, so then it would be, so it's just a trade-off between the memory size and the number of collisions you will have. And so here we want a list. We initialize it to a set of empty lists. And this would be self.size. And for put, we'll do what we said, which is first we will get the index, which is key modulo size. But here, just to make this easier for ourselves, and then here we'll need to obtain the buckets. But to make it easier, since we do this a lot, we'll just create a function that returns us a bucket for a key. Okay, so let's call this function just bucket, and we get a key, and we need to return that bucket. So let's just take this here and return it. So here we want to return this, and that way here we can use that. So it would be self.bucket, and we need to pass the key. Okay, and now for put, what we said we need to do first is to find if the key exists already or not. So let's have a function called find, and we pass to it the bucket and key. Okay, and let's define it. So find in a bucket, find the key. Okay, and now that should give us an index, right? And if that index is different than -1, which means key already exists, right? And so what do we need to do? We need to update it. So we need the value in the bucket at that position. We need it to use the new value, and so we can just set the pair to key value. Key is the same, but value is a new updated value. Otherwise, it means it doesn't exist, and so we are free to just append to the end of the bucket the key value pair. Okay. But now we need to define our find function. So our find function just walks through the bucket, which is a list, and finds the key value pair that has this value key. So what we need to do there is just go through the bucket. So it's this will give us the index here, and this will give us the what's in there. So we just enumerate over the bucket, and we check if k that we are at is equal to the key that we are looking for. Then we found it, so we return its index. Otherwise, we didn't find it, so we return -1. So that's pretty much the find implementation. Now we need to implement get and remove. So we said that for get, we also need to find the bucket, right, that the key is in. Okay, so we get the index. Now we need to return the value if it's not, if it's present, of course. So if it's different than -1, then we can return bucket at position I. Otherwise, we need to return -1. For remove, it's similar. So we need to have bucket, which equals to the same thing that we did earlier. So just this. Then we need to have I is equal to, we need to find bucket key. And we need to check again if the value is present. Only if it's present that we need to remove it, so we delete at that position. Okay, and that's pretty much it. So now if we run this, so we need here to have, since it's a function of the class, we need to have self. And looks like we are returning here for, so this is for get, looks like we are returning, yeah, so we need to return the value, but here we are returning both the pair key value. To return the value, we just need to get position 1. And if we submit this, okay, so it passes our test cases. So this is a solution using using a list. We can do a similar one using using a linked lists. So instead of having here a list, we can instead use just a linked list. So to do that, let's just empty those out. And we need to define a node, right? So we need to define our class node. What do we need here? We need 2 things. Our initializer here needs, we can have a key value, and then we need the next pointer to the next, since it's a linked list. And now here we have the key. So this is just initialization, pretty simple. Okay. Now what should we put here? So the simplest thing to do is just to put a placeholder node, a dummy node, so that we can, when we are adding elements, we just add them to the end of the linked list. And when we traverse the entire linked list in that bucket, and we try to find the key. For removing, we find where the predecessor is, and we set the next of the predecessor to be the next of the elements that we want to remove, right? And so here, so basically with a linked list, you would have an element like this. Okay, so this would be maybe x1, x2, x3. So to remove, basically what we need to do is just make x1.next equal to x1.next, right? Because this is because if we do that, then now x1 will point to x3, because x1.next, it's this where we are pointing to, and x1.next is x3, and that way we remove x2. So this is to remove x2. So that's for removal. For get, as I said, it's pretty easy. We just walk through the linked list of that bucket, and we find the one that has the value equal to key, and we return it. Now for put is a little bit more tricky. So let's say we have a linked list with value 2, 3, and maybe 5. Okay. If what we want to insert is 6, what we want to put is 6, then, well, we can just put it at the end. But if we want so these are pairs, by the way, pairs of key and value. So this would be key, and our value, let's say, is 5, maybe. Okay, or maybe let's just have our value be some in string, just to make it easier to distinguish. Okay, so this would be maybe 5 and C. Okay. So if what we want to insert is this pair 3 and maybe D, right? Then what we need to do is find this predecessor here, right? And we can just do predecessor.next, right? Which is this one. That way we get hold of it. The other way to do it also is to get the pointer here and just modify the value. But another way to do it is to do predecessor.next is just equal to 3D, because if we do this, then it's easier to do the same implementation both for the case where it's present and the case where it's absent, because otherwise, because that for the case where let's say the value is 6, this works as well, right? Because predecessor would be here, and since it was previously pointing to null, now it will point to this instead. We of course need to make it be a list node, right? So that's why we use the predecessor instead of just the node itself, because otherwise if it's not present, the node would be here and would be none, and yeah, that's a problem. So we find the predecessor. That's why we find the predecessor, so that we can just do next, and that will work for both cases, for updating with a key that exists already and a key that doesn't exist. Okay, so now that we know this, let's do what we said here. So the first step is to initialize this to a dummy node. So let's just put a dummy node with values -1 and -1, since we know that these values, since we know that the key and value are bigger or equal to 0. And now for put, we need to find the index, right? This is similar to what we did earlier, which will be just doing key modulo the size. So we get a key, and this just returns key modulo self.size. Okay, so we get the index first, and now what should we so we said that for put we need to find the predecessor of the key. If it's there, if it's not, it will point to the last node, right? So let's implement that function. Let's use it and implement it. So find predecessor node, we'll just call it predecessor node, and we'll pass here we can also do what we did earlier, similar to what we did earlier, so that it returns the bucket instead. I think that would be easier. So this would be just self.buckets in that position. We can return that. Okay, and now that we have the bucket, we can pass it here, and pass the key, and let's define this function. So it would be find predecessor for node, and we have a bucket, and bucket is a linked list, right? And so how do we find the predecessor? So we just have, so this is the first node, right? Because that's where it's pointing to. So let's call it start. Okay, and what we do is current node starts out as the pointing to the first node, and while there is a next, right, and we didn't find the exact key, so we stop on two conditions. Either we have 3, let's say here, and we are at a node that has the same key, or we are at the end, which means that the predecessor.next is equal to null. So either that, or the predecessor.next key is equal to the key we are looking for, right? And so we stop when one of these two conditions are true, and so we need to keep looping while they both are true. right? We stop when one of the condition is false, and so we need to continue looping while both are true, which is this dot key is different than the key we are looking for. Okay, so this one is to catch the case where a key already exists, and so we need to return the predecessor of that key. And this one is to catch the case where the key doesn't exist, and so we need to return the predecessor as the last node, essentially. And so here we do current is equal to current.next. We keep advancing until we reach where we are looking for, and then we return current. And this would be our predecessor here. And now what we can do is just say predecessor.next is going to be equal to list node on key value. So this makes it easier that makes it so that we don't need to handle both cases separately. And now for get, similar thing, we need to get our bucket, and we need to find the predecessor node. And then what should we do? We want to return the value, and so the value is just predecessor.next dot value, right? But what if it doesn't exist? What if the element is not in the list, right? Is not in the map. So we need to handle that case. So we have the value only if predecessor.next exists, because that's the element we are looking for, and the key is equal. We actually don't need to check if the key is equal. We can just do if this exists, then we can return the value, right? Otherwise we can just return -1. Okay, now what about remove? So for remove, again, we want to find the bucket, and we want to find the predecessor node, and then to remove the element here, we said is just we point the next to the one after it, so that we get rid of this x2. And so to do that, we just say here predecessor.next is going to be equal to predecessor.next.next. But this is valid only if this here exists, right? And so we need to check that. So if that exists, then we can do that. And then if not, we return -1. Sorry, we don't need to return for remove. And that's pretty much it. Did we implement find? Yes. So let's call this bucket actually, and let's remove this. We don't need this one. Okay. Okay, so that's pretty much the implementation for linked list case. Let's run it. Okay, looks like there is something missing in line 2 here. Okay, so it's just this. Let's move this up since it's a comment. Okay, so here we need start and the key and self here. Okay, let's. So yeah, actually there is an error here because we shouldn't do predecessor.next on list node here, because if we do that, then we get rid of the previous next. So if we do that like this, then 3 will no longer be pointing to 4C, and so we get rid of, if there are more nodes here, then we get rid of all of that. So we mess up our linked list. So actually what we need to do here is, sadly we have to check. So we have to check if it exists, right, and the predecessor key is equal. So we have to check the presence key. So if it's equal here, so key already present, then in that case we need to do predecessor.next.val is equal to value. Okay, so otherwise it's a new, we are at the end of the linked list, so we can just add, there is no additional nodes that we will lose if we do this. So now if we run this, okay, so that passes. Let's try to submit. And that passes test cases. So you can see the linked list solution is slightly more error prone just because of all the pointers. But yeah, at least for it, for example, we remove takes of n being the size of the linked list, which is the overall number of elements divided by the bucket size. A similar thing for remove, just because of the find. Same thing for get, and same thing for put, right? Yeah, so that's pretty much it, I think, for this problem for today. Please like and subscribe, and see you on the next one. Bye.